Okay, welcome back to the special topics of semiconductor technology. Today we'll discuss Chapter 2, Introduction of IC Fabrications. The objective of Chapter 2 is the following. First, we are going to define what is yield and explain its importance. The yield has something to do with the cost and the profit. The higher the yield, the more the profit. No yield, no gain, and we need to define what is yield. And then we'll describe what is the basic structure of a clean room. Clean room is the environment where IC fabrication occurs. And we'll define what is the clean room protocols. And then we are going to explain the chip packaging and introduce the so-called wire bonding and flip chip bonding processes. This is the process flow we have seen in the last lecture. To the left, you have raw materials, including electronic materials, chemicals, acid, gas, etc. You have wafer, and then mask from the design house, where your electronic design layout was transferred to the mask. All the material comes into the big block at the center here. This we call front end. Okay, this is the process in the fab we call front end. To the right over here, once you finish the front end process, we send it to the back for packaging and testing. This is called back-end process. For TSMC, its role plays here. When the raw material comes into the fab, TSMC performing hundreds of steps, including metallization, mechanical polishing, thin film deposition, etch process, ion implantation, thermal process including annealing, including diffusions, and also photolithography process. These 7 blocks at the front end process is a major process. You have a lot of minor process included. So for an IC fabrication process, it will take several hundreds of steps to finish the IC fabrication. Once you finish IC fabrication, all the IC was sent to the back-end process for testing and packaging. So after passing through all the tests, then we can go to the customer here. Let's look at the cost of running a fab. Over here we use 8-inch fab as an example. The construction of an 8-inch fab costs more than $1 billion US. Fab is very costly. The primary reason for high cost is because of clean room as we mentioned, clean room is the environment where the IC process fabrication takes place. And also the equipment is very high cost, normally more than $1 million per tools. All the material used in IC fabrication is very high in purity, sometimes it's ultra high purity. A lot of facility required to run the fab, especially a lot of training for engineering is required to have a good process control, and the pay to the engineering also is at a very high cost. So that run a fab is a very high cost process. Over here, let's look at what called so-called wafer yield. We define the so-called yield. Yield over here divided into three categories. The first is so-called wafer yield. The wafer yield is the ratio between number of good wafer after finishing all the process steps and total number of wafer for IC chip fabrication. So that's a good wafer to total wafer. The ratio between these we call wafer yield. On top of a wafer, you have die. Okay, all those tiny area, tiny square, tiny rectangle here is called a die. So we have wafer yield, and next we are looking at the die yield. The die yield is defined by the ratio between good dies, number of good die per good wafer after finishing all the process steps, to the number of total die on that wafer, and this is called die yield. Once all those die are finished process, good die being cut off to bring to for packaging, and that we'll call the packaging yield. And the packaging yield is the ratio between good chip after the process, all process, the good chip to the total number of chips. This is called packaging yield, YC. That wafer yield is basically depend mainly on processing and wafer handling. Careless human handling and the robot malfunction or miscalibration can break the brittle silicon wafer. A faulty process such as misaligned photolithography followed with edge or ion implantation, wrong dopant concentration, poor uniformity, or large amount of particle on wafer, etc., can also ruin the wafers. For the die yield, is related to the factors such as particle contamination, process maintenance, and total process step. The more process, the lower the die yield. The packaging yield related to the wire bonding, quality and specification difference between the die test and the chip final test. So the overall yield here of the fab is the product of all three yields. the overall yield can determine whether or not a fab is making money or losing money. So yield is a very important factor to determine a profit margin of a fab. Here is an example. Let's look at whether or not a fab is making money. First, let's look at the cost. The cost of a process including three parts. First is the material, wafer. For example, an 8-inch wafer costs about $150 per piece. For the process to finish the chip fabrication, it takes, say, 600 steps. Each of step costs $2. So for each of the wafer, each of step costs $2. 600 steps total up $1,200 per wafer. And the good chips, good dies sent to for packaging process. Each of the chip costs $5 for packaging. For each of the wafer, you can have up to about 200 chips. So that means for the packaging process would be $5 per chip, total about 200 chips. So that would cost you about $1,000 for packaging per wafer. Okay. Once the chip is packaging, if a good chip is packaging and you can sell to the customer, say $50 per chip. So you are going to end up with $10,000 per wafer sales amount. So let's look at here. If you have 100% yield, all the chips and packaging are good, so the total cost of the production will be $150 per wafer, $1,200 for the process fee, and the chip packaging for 200 pieces of chips, $1,000. The sum up, that would be $2,350 per wafer for IC fabrication. If that's a 50% yield, that means only 50% chip is good. Wafer cost is the same. The process is the same. And you only have 100 chip for the IC packaging. So that'll be $500. So the cost of per wafer process would be totally $1,850. If no yields at all, no yield, no packaging required, so the cost will be the wafer and the process fee $1,200. So that will be $1,350 per wafer. That is the cost for 100% yield, 50% yield, and 0% yield. What about the sale? If you have 100% yield, 200 chips are packaged and sell $50 per chip. So you end up $10,000 per wafer you sell, total sale. If that's 50% yield, only 100 chips is good. So you got $5,000 sale. No yield, no chip, no sale, 0 sales. So what is the profit margin? If it is 100% yield, The the sale is $10,000. The cost is $2,350. So you end up with profit $7,650 per wafer. If it is 50% yield and you only have 3,150%, $50 per wafer, less than 50% of the 100% yield. Again, no yield, no sales, and then you will be lost of your wafer and process fee. So you can see here, the higher the yield, the higher the profit margin here. So higher yield is the goal to pursue for each single step process. So here comes a question. If the yield for every process step is 99%, it's pretty high from quality control point of view, 99%. What is the overall process yield after 600 process steps? For each one of the process steps is 99%. Looks like very good. But for an IC fabrication process, it takes 600 steps. So the overall yield will be 99% times 99% 600 times. So that means your overall yield is 99% to the 600. It end up equal to 0.0024. That means 0.24%. Basically, no yield. No yield, no profit. You lost all your cost, wafer cost, process cost. So that means during the IC fabrication process, it took so many steps to finish IC fabrication. So each single one of the steps should have 100% yield as the goal. That way you can make money for a fab. The so-called throughput. Throughput is the number of wafers able to process, the so-called throughput. For a fab, in a fab, every month, how many wafers being processed in a fab is called throughput. Say 10,000 wafers per month. But for a single piece of tool, how many hours wafer can be processed is a throughput. Typically, say 60 pieces of wafer can be processed for an hour. That's a throughput. If you have high yield for each of the steps, if you have high yield, high throughput, that can bring you large profit margin. The most important thing is the yield. Okay, the most important thing is the yield. No yield, no profit. The higher the yield, the higher the profit margin. This is we so-called cost and yield. And if you have defect on your wafer, and that can also influence your yield. And the yield is approximately can be described in the following equation. The yield is proportional to the 1 plus D times A to the N And where Y is the yield, overall yield. D is the density of the killer defect. A is the chip size. Okay, A is the chip size. N is the number of process steps. So based upon this equation, if you try to achieve 100% yield, then the killer defect density should be 0. Okay. If you try to have Y equal to 100%, that means 1 equal to 1. So over here, killer defect should be 0 for every single process step. If you have the same defect density, that means you fix D, the D density is fixed, and the chip size A, the chip size also fixed, then the more the process here, the lower the yield. Okay, so let's look at it again. If you have fixed number of D density and the chip size here, this is fixed. The higher the number of process steps, the lower the yield. Okay, the more the process step, the lower the yield. It also indicates that if you have same defect density level, the larger the size A, the larger the size, the lower the yield. So based upon this equation, the yield, killer defect density, and chip size, and the number of process steps has big influence to the yield. Also, if you have the killer defect here, all these 5 killer defects fixed in the same position on a wafer. If you have a smaller die size, that die size equal to the A in the previous equation. The smaller die size, that will give you higher the yield. Large die size resulting a lower yield. Okay, so let's look at the equation here. D is fixed, the density is fixed, and then larger the A, larger the die size, lower the Y. Smaller die size, the higher yield. Okay, over here shows you the result. So when you're reducing the die size on a same single wafer, you can actually increasing the yield. So that means if you can improve your technology, then you actually increase your yield, increase your profit. That's why the company keep pushing the technology to a smaller feature size, so that can reduce the die size, therefore increase the yield, increase the profit. Okay, on the wafer, okay, the traditional wafer, the configuration of wafer, you can see there's a test die on different location, and basically all the process, the QC process taking on the test die. So eventually all these test die are not going to for packaging process because during the testing, the IC quality may deteriorate. Okay, so basically test die is not going to be cut and go to the packaging process. When you have your technology improve with a very small feature size, actually the scrape knife, when you cut the wafer, cut the die, the knife you cut actually can contain some of the fine test structure. So you don't need to have the test die. Over here you have 5 test die, which will be waste, become a waste. Okay, but over here you can using the scribe knife over here to design some of the test structure. So your test structure actually eventually you are going to be cut off. So all the die here, all the die on the wafer can be used for packaging if they are all good dies. So in this case you can increase the number of die produced, so you can increase the profit, reduce the cost. Okay, this section we will stop here. So for chapter 2, in the first part we discuss the concept of yield, concept of the cost of a wafer. So you know what is the yield. The yield is equal to the product of 3 yields: wafer yield, die yield, and packaging yield. And we also talk about the size of the feature, okay, the size of die, and the density of the killer defect has something to do with the resulting yield. Okay, so this would be the first part of the chapter 2. Okay, see you next week.